In science, excitement is common, relief is rare. But when astronomers confirmed the discovery of 2I Borisov in 2019, the dominant emotion wasn't shock or fear. It was something quieter, relief. Because 2 years earlier, the first interstellar object ever detected had left scientists with more questions than answers. And for a field built on predictability, that uncertainty lingered. In 2017, Oumuamua entered the solar system without warning. It was fast, it was faint, and it behaved in ways that defied expectations. It showed no clear coma, no obvious tail, no familiar cometary signature. Worse still, it appeared to accelerate without a visible source of propulsion. That acceleration sparked intense debate. Some proposed exotic natural explanations. Others questioned whether existing models were incomplete, and a small but loud fringe went further. The result was not consensus, it was confusion. Oumuamua wasn't unsettling because it was strange. Science encounters strange things all the time. It was unsettling because it offered too little data. By the time telescopes were pointed in its direction, it was already leaving. There was no opportunity for prolonged observation. No chance to test hypotheses against evolving behavior, which meant every explanation remained tentative. For 2 years, interstellar space felt unpredictable. When 2I Borisov was discovered in August 2019, astronomers immediately noticed something different. This object wasn't slipping away. It was bright enough, slow enough, and early enough in its approach to allow detailed study. But more importantly, it behaved exactly as expected. From the moment observations began, Borisov showed a clear coma. Gas and dust surrounded its nucleus. A tail formed naturally as it approached the sun. This wasn't chaos. This was familiar physics. To the public, normal sounds boring. To scientists, it's invaluable. Borisov followed the rules. Its activity increased with solar heating. Its gas emissions matched known sublimation processes. Its trajectory made sense. There were no unexplained accelerations, no missing mechanisms. After Oumuamua, this mattered enormously, because it suggested that the earlier mystery wasn't the rule, it was the exception. For decades, astronomers had simulated what an interstellar comet should look like. Those models predicted a volatile-rich nucleus, a visible coma, predictable gas chemistry, gradual evolution near the sun. Borisov matched those predictions almost perfectly. Its high carbon monoxide content even aligned with expectations for a comet formed far from its home star. This was confirmation, not contradiction, and confirmation restores confidence. You won't find dramatic quotes from scientists celebrating Borisov. That's because relief in science is subtle. It shows up as fewer speculative papers, more agreement across teams, narrowing ranges of explanation. Borisov allowed researchers to recalibrate, to say quietly, our understanding still works, and that matters more than headlines. Every field needs a baseline, a reference point. Borisov became that reference for interstellar objects. It showed what a normal interstellar comet looks like when everything behaves as expected. And once you have that, anomalies become clearer and more meaningful. Without Borisov, Oumuamua might have rewritten physics prematurely. With Borisov, it became a puzzle, not a paradigm shift. Equally important as what 2I Borisov did is what it did not do. It did not challenge fundamental physics. It did not require new forces or exotic mechanisms. It did not behave erratically or unpredictably. There were no unexplained accelerations, no missing sources of energy, no motion that demanded radical reinterpretation. Instead, Borisov followed the same rules that govern comets in our own solar system. As it approached the sun, its ices warmed. As those ices sublimated, gas and dust were released. That outgassing produced a coma and tail, exactly as decades of comet science predicted. This mattered deeply, because after Oumuamua, There was concern that interstellar objects might regularly defy our models, that our understanding of small bodies might be incomplete or fragile. Borisov showed that this was not the case. It demonstrated that the physics we rely on still works even beyond our solar system, which suggests that those rules may not be local, they may be universal. After Borisov, interstellar space felt less alien. Not because it was suddenly understood, but because it was consistent. Borisov suggested that the environments beyond our solar system are governed by the same physical principles we observe here, that the processes shaping comets, planets, and debris disks around other stars are not radically different from our own. That materials we recognize, water, carbon compounds, familiar volatiles, exist elsewhere in the galaxy. This realization quietly changed perspective. Interstellar space no longer felt like a realm of unknown physics. It felt like an extension of a familiar universe, larger, more varied, but not fundamentally hostile to understanding. That sense of continuity was grounding. It allowed scientists to shift from anxiety back to curiosity, from uncertainty back to investigation. Borisov didn't just calm a debate, it reshaped priorities. Once scientists had a clear example of a normal interstellar comet, they could refine how future discoveries would be approached. Survey strategies improved, focusing on earlier detection. Observation protocols were adjusted to prioritize long-term monitoring. Expectations became clearer and more realistic. When future interstellar objects are detected, they will not be compared first to ʻOumuamua. They will be compared to Borisov, because Borisov showed what ordinary looks like when material from another star system passes through ours, and having a definition of ordinary is essential. It allows anomalies to be identified clearly and evaluated carefully without rushing to conclusions. Borisov did something remarkable by doing very little. It arrived from another star system, followed the rules we already understood, and quietly continued on its way. In doing so, it reminded scientists of something easy to forget during moments of uncertainty. Not every mystery overturns understanding. Some restore it. Some confirm that our models are resilient, capable of extending far beyond the environment where they were first developed, and holding together even when tested against material born around another star. That reassurance matters. Because as our surveys improve and our instruments grow more sensitive, interstellar visitors will no longer be theoretical curiosities. They will be part of our ongoing observations. And when the next object appears, we won't be starting from confusion. We'll be starting from context, from comparison, from everything Borisov quietly taught us. If you want to follow these discoveries as they unfold, grounded in real data, careful analysis, and long-term perspective, subscribe to our channel. Because understanding doesn't advance only through surprises, it advances through confirmation. And the next discovery will only make sense because of what we already know.